Hello students, welcome to the 13th lecture in partial differential equations. So as promised in the previous video lecture, in this class also we will discuss few more questions which are based on type 4 which is used to solve the partial differential equations. And the first question for the day is p plus q equals to x plus y plus z. So the first step for this question is we have to always write the Lagrange auxiliary equation. So the Lagrange auxiliary equation corresponding to this will be dx upon 1 is equals to dy upon 1 is equals to dz divided by x plus y plus z, right? And now if I compare the first two fractions, so that is dx upon 1 equals to dy upon 1, so that is nothing but dx equals to dy, right? And now if you integrate on both sides, what do I get? I get x equals to y plus c1, or x minus y equals to some c1. Mark this as equation number 1, right? And now in order to find the second set of solution, what I'll be doing is I'll be using the Lagrange multipliers, and corresponding to this, that is 1 1 and 1. So just observe what will happen if I choose the Lagrange multipliers to be 1 1 1. So this thing will be equal to dx plus dy plus dz, and in the denominator you will be getting 2 plus x plus y plus z, right? Now one thing which you need to observe from here is, in the numerator we can write it down derivative of x plus y plus z, right? Because this will be dx plus dy plus dz divided by 2 plus x plus y plus z. But now this 2 is not disturbing me. Why? Because the derivative of constant is 0. So I will say the derivative of 2 plus x plus y plus z divided by this, right? Because they both are exactly equal to each other. So what I'm saying is, this thing and this thing, they are exactly equal to each other, right? So now this is the function, derivative of function divided by the function. So that is nothing but the log of function, right? So now if I compare this with the first one, so that is, now what I am doing is dx upon 1 is equals to derivative of 2 plus x plus y plus z divided by 2 plus x plus y plus z. And now if you integrate on both sides, so just see what do we get? We get nothing but x equals to log of 2 plus x plus y plus z plus some log of constant c2. Now just apply the properties of log. So this is nothing but log of, that is 2 plus x plus y plus z multiply with c2, right? And now just, we have to vanish this log. And how can I vanish this log? This is nothing but 2 plus x plus y plus z into c2 equals to e raised to power x. Simple. And now take constant on the other side and bring exponential on the left side. So this will be 2 plus x plus y plus z multiply with e raised to power minus x equals to some constant c2 prime, right? Where c2 prime is nothing but 1 by c2. Again a new constant. Now this is my equation number 2. So already we have found the first equation, that is x minus y equals to c1. The next one is this. So the final general solution, so that is phi of x minus y comma 2 plus x plus y plus z multiply with e raised to minus x equals to 0, where phi being an arbitrary function. So I hope this question is clear to you now. Now let me to take one more interesting problem. So the second question for the day is, so write down the second one. So that is, if I say px multiply with x plus y, right? So this is minus y times x plus y multiply with q equals to minus of x minus y into 2x plus 2y plus z, right? Now the first step, as usually, so the first step is very trivial. You have to find the Lagrange auxiliary equation. So that is nothing but dx upon x into x plus y equals to dy upon minus y into x plus y. This thing is equals to dz upon minus of x minus y into 2x plus 2y plus z, right? And now if you just compare the first two fractions, so if you compare the first two fractions, so just observe what do you get. So this is dx upon x into x plus y is equals to dy upon minus y into x plus y. So this x plus y and x plus y gets cancelled out, right? So what do you get? So this is dx upon x equals to minus dy upon y. And now if you integrate on both sides, so this is nothing but log of x is equals to minus log of y plus some constant log of c1. Now just bring it on the right hand side. So this is log x plus log y is equals to log c1, right? Apply the properties of log. So this is nothing but x into y equals to c1. So that is the first solution for the equation. And now we are going to work for the second solution. For that, what do I say? I just say, so just let me to rewrite this equation once again. So the corresponding Lagrange auxiliary equation was this. So now what I am doing is I'm just saying, so just do dx plus dy, right? If you just do dx plus dy, what do you get? So this is x times x plus y minus y into x plus y. And furthermore, what you are interested to do is dx plus dy plus dz. So you will get a very beautiful thing. So just observe, try to observe the things. So this is, I'm just writing all the terms from the numerator one, right? And minus x minus y multiply with 2x plus 2y plus z, right? So now just observe one more thing. So if we now work on this term, that is dx plus dy upon this, right? Can you see something is common in this? Yes, x minus y is common. Sorry, x plus y is common, right? So dx plus dy divide by x plus y into x minus y. Am I clear? Right? But in the denominator of the next term, what you can see is x plus y is common. So this is dx plus dy plus dz. And mind it is only common from the first two terms. So this is x plus y, and here it is x, and here it will be y, right? Minus this into this. And now throughout you can see that x minus y is common, right? So in the next step you can write it down. So that is dx plus dy plus dz divide by, so x minus y is common throughout. Yes, you can see this is x minus y, this is x minus y. So you can take it out common. So this is x minus y. In the bracket, x plus y minus 2x minus 2y minus c. And in the left hand side, so we have dx plus dy divide by x plus y into x minus y. So one thing is very obvious, we all want to do, that is x minus y gets cancelled out with x minus y. What next? The next one is dx plus dy. So that is the derivative of x plus y divide by x plus y. So this thing is clear, very beautiful thing, right? And in the right hand side, so this is dx plus dy plus dz. Now just see to this, x minus 2x, so that is minus x, y minus 2y minus y minus z. And now if you take minus to be common, so this will be plus plus plus, right? And in the numerator also you can say that this is nothing but derivative of x plus y plus z. And now if you integrate on both sides, what do you get? So this is nothing but the log of x plus y, right? And here we have a negative, so you can bring it on the one side, right? And here it is 0, so this will be plus log of x plus y plus z is equals to some log of c2. Apply the properties of log, and finally what do we get? We get x plus y multiply with x plus y plus z equals to c2. Mark this as equation number 2. Already we have found the equation number 1, and this was the equation number 2, and hence the final, so the general solution is, so that is phi of, so the first one was x into y, right? Just see again. So this was x into y equals to c1, and the second one, that is x plus y multiply with x plus y plus z, right, is equals to 0. Again you have to mention it out, where phi being an arbitrary function. Right, so that is how we will proceed in this question. Moving on to one of the interesting problem in this category of questions, so that is px multiply with, so you all should note it down, z minus 2y square, right? So this is equals to z minus qy multiply with z minus y square minus 2x square. So that is the question for the day. And now in order to solve this question, what we will do is, firstly we will convert it into a beautiful form, so that we can write the Lagrange auxiliary equation. So the first step will be, so this is x times z minus 2y square multiply with p. Now the first one is P plus Q, right? You should remember this is equals to R. You have to convert it to this format. Yes or no? Now if you multiply these terms with this one, so that is Z times this thing minus qy times z minus y square minus 2x square. So they are equal, right? And in the next step now what you will do is x times z minus 2y square multiply with p, and where is the q term? Observe this thing. So here we have the q term. So plus q times or plus y into z minus y square minus 2x square multiply with q equals to z times z minus y square minus 2x square. Now this is a beautiful form. Now we are capable enough to write the Lagrange auxiliary equation. So the corresponding Lagrange auxiliary equation will be, so this is dx divided by x times z minus 2y square. And this thing is equal to dy divided by y times, so this is z minus y square minus 2x square, right? And this thing is furthermore equal to dz divided by z times, so z minus y square minus 2x square. Now we have got the Lagrange auxiliary equation, and now we can proceed for the further steps. So one thing is very much clear: if we take the last two fractions, so just observe this thing very carefully. If we take the last two fractions, you can see y minus, so z minus y square minus 2x square will get cancelled out. So you are left with this dy by y equals to dz by z, and this is nothing but log y equals to log z plus log of some constant c1. Apply the properties of log and get the final answer. So the final answer will be y upon z equals to c1. Mark this as equation number 1. Now the second solution will be a challenging task, right? So that was the first solution. So let me to erase this. Yeah. So for the second one, what I will be choosing is I have to choose the Lagrange multipliers now, right? And what is my assumption now? What are the Lagrange multipliers? So the Lagrange multipliers here are 0, minus 2y and 1. So observe what will happen. If you multiply with 0, so you will get 0 only. So this is nothing but minus 2y dy plus dz. Am I clear? And what will happen in the denominator? So this is minus 2y multiply with y, that is y square, into z minus y square minus 2x square, right? Plus 1 times, so this is z times z minus y square minus 2x square. Now let us quickly solve the denominator part first and see what the things will get common, and whether it can be converted into some beautiful format or not, right? So this is minus 2y square multiply with z minus y square minus 2x square, right, plus z times z minus y square minus 2x square. So we are interested to solve the denominator part first and just observe if we get anything beautiful in the denominator part. So let's resolve them. So we can clearly see that this thing, that is z minus y square minus 2x square, is common. So just take it out common. So this is minus 2x square, and in the bracket we have z minus 2y square. So in the numerator we have minus 2y dy plus dz. And can you tell me what this thing can be written as? Derivative of what? Just observe this thing. So clearly we have to write dz. So you have to include z. So because from this portion you will get dz. And how to get minus 2y square now? So that is the next step which you have to think. So just observe, this is minus y square. Because what will be the derivative of minus y square? So this will be minus 2y dy. Am I clear? So the numerator is nothing but derivative of z minus y square. So let me to finalize all the things, club all the things. So on clubbing all the terms, what do we get? So derivative of z minus y square divided by z minus 2y square multiply with z minus y square minus 2x square, right? And now if we compare with the first one, so that is dx divided by x into z minus 2y square. Now just observe, z minus 2y square will get cancelled out, right? Z minus 2y square, z minus 2y square will get cancelled out. And what do we get? So this is derivative of, so z minus y square, bring dx in the denominator, so this thing is equals to z minus y square minus 2x square whole divided by x, right? Now one more step, so that is derivative of z minus y square divided by d of x is equals to z minus y square by x minus 2x square by x. So this is nothing but that is minus 2x. So this is z minus y square by x, and these terms were equal to derivative of this thing divided by dx. And now if I substitute z minus y square to be u, so what will happen? So this thing will be du by dx, right? And this will be u upon x is equals to minus 2x, right? And now if you bring all the terms on one side, so that is du by dx minus 1 by x times u equals to minus 2x. Isn't it of the form dy by dx plus py equals to q, right? Where p and q, they were the functions of x. Yes or no? So this is of the form of the ordinary linear differential equation. So this is nothing but the ordinary linear differential equation. And all of us know how to solve this now, right? We have to find the integrating factor and just, solve it out. So what is the integrating factor? So integrating factor is e raised to power, right? So that is 1 by x, that too of negative, yes, with respect to x. And what is 1 by x dx? So that is log of x, so minus log of x. And you can take minus 1 in the power, that is by the property of log, right? And e and log will get merged, so this is x raised to minus 1, so that is nothing but 1 by x. So 1 by x is the integrating factor. And how do we write the final solution? So final solution is given by, so u multiply with integrating factor is equal to integration of the right hand side q, that is minus 2x, multiply with integrating factor into dx plus some constant c2. So that is how we used to write the solution of the first order linear differential equation, right? So this is nothing but, now x and x get cancelled out. So what is this integration? So minus 2x plus c2 equals to u upon x. And what is the u? Now just substitute the value of u. So this is z minus y square. So u is z minus y square divided by x is equals to minus 2x plus c2. Mark this as equation number 2. We have already found the first solution, that was from the equation number 1, already marked here, right? And the final solution can be given up. But before that, let us bring constant on one side and all other terms on the other side so that we can easily club the terms. We will do z minus y square divided by x plus 2x equals to c2. Now mark this as equation number 2, and the final solution that can be written as phi of y by z comma z minus y square. Now this is totally your choice whether you want to solve it out and write all the terms, or you just want to write the solution as it is. So this is plus 2x square divided by x. So that is also one of the way you can always write down the solution, right? So this is equals to 0, where phi being any arbitrary function. So I hope this concept to solve the partial differential equations is clear to you now. So we have given more than like 12 or 13 lectures on this particular section of partial differential equations. So in the upcoming video lectures, we will start a very important topic, that is the Cauchy problem. So in the next topic, we will deal with the Cauchy problem. What was the problem, what is the origin, and what kind of solutions we are going to get from this. So that is all what we will be learning in the next video lectures. Till then, stay tuned, and for more such videos, do subscribe to our YouTube channel and do not forget to press the bell icon. Thank you so much, students. Thank you.